Good morning and welcome to today's lecture. We have been discussing the thermal history of the universe, and at the end of the last class we were discussing the possibility of the neutrino having a mass. So, let us resume that discussion and let me remind you of what we were discussing. So, we started off by noting the fact that the photon number density in the universe is 420 photons per centimeter cube at present, and the number density scales as 1 plus z to the power 3. Then we remember that the neutrino number density is lower than the photon number density, and since the neutrinos are fermions, the number, if the temperature were the same, then the number density of neutrinos would be 3/4. For every species, every flavor of the neutrino, the number density would be 3/4 times the number density of photons if the temperature was same, but the temperature also is lower. So, finally, the number density of neutrinos is 3/11 of the number density of photons. So, in addition to the photon background, we also have a neutrino background, and each flavor of neutrino has a number density of approximately 113 into 10 to the power 6 per meter particles per meter cube, and the whole thing scales as 1 plus z to the power 3. So, given this number density of neutrinos which is present in the universe, we were considering the possibility that one of the neutrino flavors, one of the neutrinos has a mass. So, one flavor of neutrino has a mass. This is the assumption that we had made, and we had also assumed that the mass is much smaller than the temperature scale where the neutrinos decouple. So, the temperature scale where the neutrinos decouple, we had seen, is around 10 to the power 10 Kelvin. So, if you convert this to a mass scale multiplied by the Boltzmann constant, this will give you energy divided by c square, it will give you a mass scale. So, the mass of the neutrino is assumed to be much smaller than this number. If this holds, then the fact that the neutrino has a mass may be completely ignored at the time where the neutrinos decoupled from the rest of the components of the universe. So, at the time of decoupling, the neutrinos, the number density of neutrinos would be exactly the same as this, except that the redshift would be different. And with the expansion of the universe, the number density would scale, the phase space distribution of neutrino would be frozen, and all that would happen is that all the each momentum would scale, would go down inversely with the expansion of the universe. We have studied this. So, for once the neutrinos decouple, all that happens is that the neutrinos free stream, and the density in phase space is frozen, and each momentum essentially scales as 1 by a, and so that is what would happen. Now, the mass that we have considered, although it is much smaller than the energy scale 10 to the power 10 Kelvin, we have assumed that it is more than the energy scale at present, and so it is more than the present energy scale. This should actually be the neutrino temperature, which is somewhat lower, but it really does not matter. So, we are assuming that the mass is more than the present energy scale. So, the neutrino becomes, the mass of the neutrino manifests itself sometime in the as the universe expands, and at present we assume that the neutrino is, the rest mass energy of the neutrino is much larger than the kinetic energy. So, at present the neutrino is a non-relativistic particle, its energy is dominated by the rest mass, and so since the energy is dominated by the rest mass, We can calculate the mass density of the neutrino also. It is just the mass of each particle into the number density of particles. So, this is the mass density of that massive neutrino species at present, which is predicted for such a neutrino. And these particles, their random motion is also going to be negligible. They are essentially, the energy is dominated by the rest mass. So, they do not contribute significantly to the pressure. You can think of them as pressureless dust, which we have encountered earlier. So, this is the consequence of there being one neutrino flavor which has got a mass. So, you will have a neutrino density like this. It predicts that the universe will now have a neutrino density, a matter component which has density given by this. Now, let us ask the question, is there any observation that seems that are there any observational constraints on this? Can the universe be at present, can there be such a matter density in the universe coming from neutrinos? Well, there are observations which, some of which we have discussed and some which we have not, but these observations tell us that the matter content of the universe, omega matter naught, is of the order of unity or less basically. So, it would be more appropriate to put a so, the matter content of the universe at present is predicted to be less than the density parameter of matter at present is predicted to be less than 1. We have seen that there is dark energy, etc. So, there are observations. From the expansion of the universe and various other observations, which indicate that the density parameter of matter in the universe at present is less than or equal to 1, which essentially tells us that if one species, one flavor of neutrino is massive, then the density of that neutrino should be less than equal to the critical density of the universe, or we can say that this should be equal to rho critical naught into omega matter naught. And the critical density of so we have worked out what this would be in terms of the neutrino mass. What this essentially tells us that the neutrino mass m nu into 113 into 10 to the power 6 meter minus 3 should be less than equal to the critical density of the universe. The present value of the critical density of the universe is 1 point. We know that the critical the critical value is 3 of the density is 3 h naught square by 8 pi g, and if you write h naught in terms of 100 small h kilometers per second per megaparsec, then the value, then what this gives you is that the critical density at present is 1.88 into 10 to the power minus 26 kg h square. This h square comes from here, kg per meter cube, that is the critical density. So, the density of neutrinos coming from the neutrinos should be less than the matter density universe. So, the matter density is the critical density into omega matter naught. So, what it tells us is that m nu, the mass of the neutrino, should be less than equal to. So, we can divide this by 113 into 10 to the power 6 to get a limit on the mass of the neutrino, and what it tells us is that this should be less than 1.7 into 10 to the power minus 33, 10 to the power minus 34, sorry, kg into omega baryon h square. So, this is the constraint that we get on the mass of the neutrino. It is more meaningful to express this in terms of electron volts. So, what we have to do is we have to multiply this by convert this into energy multiplied by c square. So, we have to multiply to convert to EV electron volts, we have to multiply into c square by E, that is what you have to do. So, the limit that you get if you do this is that the mass of the neutrino should be less than or equal to 94 electron volt omega matter naught h square. So, this is the limit that you get on the neutrino mass from the as a limit from the fact that the mass density parameter of the mass of the universe should be less than or equal to 1. So, from the fact that you know you can determine the mass parameter of the universe. So, the mass of any neutrino, if one of the neutrino species is flavors is massive, the mass should be less than 94 electron volts, of the order of 94 electron volts. This so the basically what we find is that observations, cosmological observations of the expansion rate of the universe and the large scale structures can put limits on the masses of fundamental particles, in this case the mass of the neutrino. And this very interesting limit, this very interesting idea was first worked out by in 1972 by Kousic and McClelland. And when it was initially worked out, this was one of the most sensitive, most stringent limits on neutrino mass. Now, let us ask the question, you see, what happens if one of the neutrinos is species is actually massive. So, if one of the neutrino species is actually massive, then we have the whole universe is filled at present filled with these massive weakly interacting particles. Which are also referred to as WIMP. So, these are particles which do not interact with photons. And interact weakly with electrons and baryons. So, these such particles would essentially be only the only visible manifestation of such a particle would be through the gravitational force, gravitational interaction. The gravitational field, the gravitational interaction produced by such particles would be just like any other particle, but these particles would not emit light, they would not interact with photons, and they would only interact very weakly with electrons and protons and neutrons. So, these such, if we had such a sea of such particles floating around, which would happen if one of the neutrinos were massive, this would be what a very good candidate for what is called dark matter. And we have already discussed one evidence for dark matter, that is the rotation curve of galaxies, and there are a variety of other observational evidences which indicate that the universe at present is has a large component of the matter in the universe is at present made up of this kind of matter, which is dark matter. So, the question arises, are neutrinos the dark matter that we have in the universe? I have told you that there is evidence that around 25% of the matter of the constituents of the universe are dark matter. So, the question, natural question that arises is that are the neutrinos, are massive neutrinos dark matter candidates? Well, let us see what this is the limit that we have using the kind of arguments which were given in 1972. Let us now briefly, very briefly, just look at the current situation. So, let us ask the question, what are the limits on the current limits on the neutrino mass? Well, the first point that I should tell you is that there now are very stringent limits on the neutrino mass, very stringent limits which are imposed by various other kinds of experiments and observations. So, let me briefly just tell you about some of these. So, the first limit, the first kind of limit comes from observations of neutrino oscillations. So, observations of neutrino oscillations, and neutrino oscillations are observed in neutrinos coming from the sun. So, solar neutrinos, nuclears, then from nuclear reactors, and from cosmic ray showers. So, what are these neutrino oscillations? Well, I have told you that there are three different flavors of neutrinos. So, these are the electron neutrino and the mu neutrino and the tau neutrino. So, what happens in neutrino oscillations is that as the neutrinos propagate, if you start off with electron neutrinos, it will slowly become mu neutrino and maybe tau neutrino, and then again come back to electron neutrino. So, the neutrino oscillates between these three flavors, and the measurement of neutrino oscillations, these oscillations have been measured from neutrinos coming from the neutrinos coming from the sun, in neutrinos coming from nuclear reactors, and also in neutrinos coming from cosmic ray showers. And these neutrinos, the observation of these oscillations impose limits on the mass difference between the mass states of the neutrinos which have well defined mass, between neutrinos states with well defined mass. And these states with well defined mass do not correspond to the electron mu and tau neutrino, which is why we have oscillations between these as the neutrino oscillates. And what this so let us give it a name, let us call it delta m square. So what it tells us is that so these neutrino oscillations tell us that the mass difference between these states has the values. So there are two values, two limits. So one is 8.0 minus 0.4. These are experimental limits, error bars, and rather plus minus 0.4 plus 0.4 and minus 0.3 into 10 to the power minus 5. So this is one limit, and the other limit is 10 to the power that the mass difference should lie in the range minus 1.9 into 10 to the power minus 3 to 3 into 10 to the power minus 3. These are all in electron volts square. So there are three different states which have definite mass, and the difference in the mass square between these three states, one of them is known to be 8 electron volt square, other one is in this range. So these limits tell us that the mass difference between the neutrinos is extremely small. And there is no reason the mass difference between different neutrino states is extremely small, and one believes that the masses themselves also are extremely small, less than 1 electron volt. So of the order of maybe, if at all there are masses, these put limits that they should be quite small, less than electron volts. So this implies, this is interpreted as telling us that the masses, neutrino masses, also are extremely small. The other possibility is that the masses are not small, but they have an extremely small mass difference. So even if the neutrino has a mass, one neutrino has a mass, let us say 1 eV or so, then the other one will have a mass which is very close to this, because the difference in the mass square is of this order, 10 to the power minus 5. So if the neutrino, if one of the neutrino has a mass, then all three of them must have nearly equal masses. That's what it tells us. And the most natural interpretation is that all of them have zero mass or extremely small mass. So this is one of the most stringent kind of inputs that we have on the neutrino masses. Then the second input which I can tell you about is that there are absence of no anomalies in the beta decay in the decay of tritium, in the beta decay of tritium. This imposes the limit that the neutrino mass should be less than 2 electron volts. The third limit which I can tell you about is also again cosmological, though these the two which we just talked about are first one. This also involves some amount of astrophysics, the solar neutrinos and the cosmic ray showers. This is purely terrestrial. The third is from the anisotropies in the cosmic microwave background radiation, CMBR. And this imposes the limit that the sum of the neutrino masses so we know that there are three flavors. So the sum of the neutrino masses should be less than 0.6 electron volt, and this is at the 95% confidence level. So at 95% confidence, the sum of the neutrino masses should be less than 0.66 electron volts. And we just saw arguments why if the neutrinos are massive, then all three of them must have nearly equal mass, because the mass differences have been measured and they are extremely small. So this imposes a limit that the mass of a single species should be less than 0.22 electron volt. So all of these together seem to indicate that the neutrinos that we have been discussing are not the dark matter. That is, they do not contribute very significantly to the dark matter. That is the so the mass limits, current mass limits, and various other observation limits seem to indicate that these neutrinos that we have been talking about are not the dark matter that we see. Rather, the dark matter that we see are not neutrinos, not the kind of neutrinos which we have been talking about. There is another mass window which corresponds to very extremely high mass neutrinos, which could be a dark matter candidate, but that does not fall within the purview of these three kind of neutrinos which we have been talking about. So let me bring this topic to a close over here. So till now what we have been discussing is the possibility that the neutrinos have mass, and we saw that astrophysical observations provide quite stringent limits on the neutrino mass, which also indicate that the kinds of neutrinos which we have been talking about, which decouple from the CMBR at a temperature of around 10 to the power 10 Kelvin, which were in thermal equilibrium before that, these neutrinos are most probably not the dark matter that we see around us. Okay. So the question, what is the dark matter, what is the dark matter really made up of, is still an open question, and let us now move on to something else. So till now our discussion has mainly of the thermal history has mainly focused on the photons, and then we considered the electron positron annihilation and the neutrinos. Let us now also discuss what happens to the small amount of baryons, nucleons, that is present. And this brings us to the very interesting topic, which is the topic of Big Bang nucleosynthesis. Big Bang nucleosynthesis. So, what we are discussing now is the small amount of neutrons and protons which are the strongly interacting particles, the nucleons. We shall sometime refer to them as nucleons and sometime as baryons. Which are present in the universe at temperatures of around 10 to the power 10. So, we have seen that 10 to the power 10 to 10 to the power 4 and higher, even higher than 10 to the power 10, these particles do not play a very significant role in the dynamics of the universe. The dynamics of the universe is mainly governed by the neutrinos and the photons, which are relativistic particles. These particles have become non-relativistic and they do not play a very important role in the dynamics of the universe. And we have essentially ignored these particles till now. And we have worked out the equations that govern the dynamics of the universe in this epoch. We shall come back to this shortly. Now, let us ask the question, what happens to the neutrons and protons, the nucleons in this epoch? Now, in this we know that there are several reactions which can convert neutrons and protons. So, these reactions, let me outline these reactions. Let me move on to another sheet of paper. So, these reactions are neutron. The neutron can interact with an positron to form a proton and a antineutrino. This is the first reaction. The second reaction is that a proton a neutron can interact with a neutrino to form a proton and an electron. And the third reaction is that the neutron can go over to a proton and a positron, an electron and an antineutrino. So, all of these three reactions essentially can convert a neutron to a proton and a proton to a neutron. And at sufficiently high temperatures and densities, these reactions are in thermal equilibrium. Now, at the temperatures that we are interested in, of the order of 10 to the power 10 Kelvin, the neutrons and protons are essentially at rest. The temperature is smaller than the rest mass of the neutrons and protons. They are essentially at rest, and the binding, the mass difference Q between these two is essentially the difference. The neutron has a larger mass than the proton, and this has a value of 1.28293 MeV, and we can, it is also useful to write this in terms of a temperature. So, what we can do is 1.293 into, this is in MeV, into 10 to the power 6 into the charge of the electron, which is 1.6 into 10 to the power minus 19, and divided by the Boltzmann constant, which is 1.38 into 10 to the power minus 23, and it gives us the temperature scale, which is 1.5 into 10 to the power 10 Kelvin. So, the energy difference between the mass difference between the proton and the neutron, the corresponding temperature corresponding to this scale is of the order of 1.5 into 10 to the power 10, which is somewhere in the range that we are talking about. Now, if these reactions are in thermal equilibrium, then the ratio in thermal equilibrium the ratio x n by xp is equal to e to the power minus the mass energy difference between the neutron and the proton, which is we have seen 1.293 mega electron volts divided by kB T, which also tells us that the so now here let me just tell you what xn and xp are. Xn, for example, is the fraction of nucleons in neutrons. Similarly, xp is the fraction of nucleons in protons. And at sufficiently high temperatures of the order of 10 to the power 10, these are the only two kinds of particles that we have, and the total sum is 1, which is why we can write it in this way. And we can then eliminate, we can solve this in thermal equilibrium. We can solve this, and it gives us that xn, the neutron fraction, is 1 by 1 plus exponential q by kB T. Now, we have discussed already that to determine if these reactions are in thermal equilibrium or not, we have to look at the reaction rates and compare them with the rate of expansion, the Hubble parameter, at this epoch. And we have already calculated the Hubble parameter. If you remember, we can use this to calculate the Hubble parameter, which we have done in the last class, during the epoch where the temperature is 10 to the power 10. And so one can, these are all weak interactions, so the reaction rates can be calculated if one knows how to calculate the weak interaction reaction rates. And these detailed calculations, they show that these reactions remain in thermal equilibrium till a temperature of 3 times (10 to the power 10 Kelvin). So, these calculations of the weak interaction reaction rates, they essentially tell us that this formula, the neutron fraction, can be calculated using this formula till a temperature, till the universe has a temperature of 3 into 10 to the power 10 Kelvin, and the corresponding age of the universe can be calculated using this. And to just give you the feel for the numbers, a detailed calculation of the reaction rates tells us that at a temperature of 3 into 10 to the power 10 numerical calculations, the age of the universe is 0.1106 seconds, and the neutron fraction xn is equal to 0.3798, which is very close to thermal equilibrium value, which you would get if you were to substitute 3 into 10 to the power 10 over here. So, at 3 into 10 to the power 10 Kelvin, the reaction rates are sufficiently high for thermal reaction for thermal equilibrium to hold. But at temperatures below this, at T less than 3 into 10 to the power 10, what happens is that at around the densities fall, further the neutrinos decouple, so once the neutrinos decouple, they do not interact much with anything else. After that, the neutrino cross section falls, and these reactions where proton gets converted into neutron, or the neutron scatters with the neutrino to form a proton and an electron, these no longer take place. So this occurs, decouples at around 10 to the power 10 Kelvin, and we also remember that around that the electron positron annihilate at around 5 into 10 to the power 9 Kelvin. So further, there are the electron density also falls, and the electron positron density falls. So these reactions also get suppressed, and so these reactions all stop. By and large, the only reaction that continues to happen beyond this is this reaction where the neutrinos get converted into protons, and let me write it down. The reaction that continues to occur is that the neutrinos, they go over to proton plus and electron plus the antineutrino. So we know that the neutron is an unstable particle. A free neutron is an unstable particle. So it essentially, once it goes out of equilibrium, the only reaction that proceeds is that the free neutrons, they decay to form the proton, electron, and the antineutrino, and this is all that occurs once the reaction goes out of equilibrium. So once you cross 10 to the power 3 into 10 to the power 10 Kelvin, once you cross this 3 into 10 to the power 10 Kelvin, essentially the neutrons all decay and get converted into protons. So this is the basic thing, and this reaction has a lifetime which I denote here by tau n of 885.7 plus minus 0.9 seconds. So this is the lifetime of this neutron once it goes out of thermal equilibrium. So this free neutron essentially decays with this lifetime, and the neutron fraction xn in this epoch can be well described by this 0.1609 into exponential minus tau by tau n. So, this is what happens. So, once the neutrinos, once the thermal equilibrium is gone, the neutron fraction, the neutrons decay to form protons, and the neutron fraction falls exponentially with time, with this with the lifetime, mean lifetime being given by this. And just to give you a feel for the numbers, remember that we had a mass we had a neutron fraction of around 0.38 at 3 into 10 to the power 10 when thermal equilibrium was last there, and by a temperature of 10 to the power 9 the neutron fraction falls to 0.133, which again is very close to check this. I should give you the age of the universe over here, and the age of the universe here is 168.1 seconds at this temperature. So, these are from detailed numerical calculations of these reactions, putting in all the nuclear weak interaction rates, etc., and it is very close to this exponential decay once the neutrons decouple. So, let me recapitulate what we just learnt about the behavior of this of the baryon species. So, there is an epoch where they are in thermal equilibrium, and this is at high temperatures, and in this epoch the neutron fraction is well described by this formula where they are in thermal equilibrium, and this I have also told you the value over here. So, one can use this to calculate the neutron fraction in all the way till 3 into 10 to the power 10 Kelvin, and beyond that, once you cross that value where they are no longer in thermal equilibrium, all that happens is that the neutrons, they decay to give protons, electrons, and antineutrinos, and in this regime, so this is T less than 3 into 10 to the power 10 Kelvin. This is T greater than equal to 3 into 10 to the power 10 Kelvin. Okay. The neutron fraction decays exponentially, and it forms the protons. Now, given this background about what happens to the neutrons and protons in this expanding background, let us now ask the question about address the issue of the formation of other elements heavier than these particles during these epochs that we have been discussing. So, the basic idea is that is a reaction of this kind. So, the question that first of all the question that we are going to ask is that can the neutron and positron fuse to form heavier elements. heavier nuclei. So, essentially in a nutshell, the kind of reaction that we are interested in is like this. So, So, what happens, the kind of process that we are interested in, the question we are asking is that Z protons and A minus Z neutrons, they fuse, they combine to form some element, some nuclei, the nuclei of some heavy element which has got atomic mass number A, and atomic number Z. So, this is the question that we are asking. So, Z protons and A minus Z neutrons, they fuse, they combine to form an element, the nucleus of an element with the mass number, atomic mass number A and atomic number F. So, this is the process that we are interested in. We will take up in the next class, we shall see consider the possibility that the neutrons and protons fuse together to form heavier elements of atomic mass number A and atomic number Z. So, let me just briefly recapitulate what we have done in today's lecture and stop after that. So, in today's lecture, we first considered the possibility that neutrinos have mass, and after that we worked out the predicted mass density then, and we saw that just the expansion of the universe puts limits on the neutrino mass. After that we addressed the question, and if one of the neutrinos does have mass, it will be a very promising dark matter candidate. But after that I showed you that there are very stringent limits now which more or less indicate that the kind of neutrinos which we are discussing are not the dark matter candidates. After that we shifted our attention to another very interesting issue. This is Big Bang nucleosynthesis. The essential question is that we know for heavy nuclei to be synthesized, we need a very hot and dense environment. The early universe, which we have been discussing, provides us with such an environment. So, the question we are addressing is what kind of nuclei can be synthesized in the early universe. And we started off with discussing the residual protons and neutrons, and we saw that these will be in thermal equilibrium till the universe is hotter than 3 into 10 to the power 10 Kelvin. Once the universe cools below 3 into 10 to the power 10 Kelvin, the neutrons will decay exponentially, and I showed you how you can calculate the neutron fraction before this, that is before 3 into 10 to the power 10 at temperatures hotter than 3 into 10 to the power 10 and at temperatures cooler than 3 into 10 to the power 10. So, let me stop here. In the next class we shall continue our discussion on the Big Bang nucleosynthesis.